lead code, as usual, we go here, and then we just like give up immediately to extract the hard or medium questions. Let's do this, and then let's go. Return all possible results in any order. Thinking DFS. Or DP. I think feel like DP or DFS. I know a string is valid if open and close parentheses are equal, and I know a string is valid if the number of close parentheses never exceed the open parentheses. So if I write a function to check, the legitimacy of this, let's say I start with the root, and if it's not legitimate, then I go DFS by if it's not legitimate, I can also output the balance of so my DFS can let's say number of minus num. So if it's positive, then we know to remove this. If it's negative, we know to remove this. And The problem is you could have 25 and, well, 20 and that's not a huge number actually. That's like a billion iterations. The other way is like DP, so I'm just trying to think if I should DFS or DP this. I guess I'll try DFS. Brute force DFS without pruning says, so if I don't return this, I just return true or false. And then so in each iteration, I just remove each one of these. And then check if it's valid. So this might not work actually with DFS, and so I thought DFS would work because you'd exhaust everything, but you could remove parentheses in a suboptimal way such that you don't remove the minimum amount of invalid parentheses and you still get a valid. So for example, you could remove this and then this and then this and then end up with this, and then that's still, quite good. So it's actually quite messy because at the top of the tree, then you need a wrapper function to basically sort out the lengths of everything. So I think DFS is the more convenient way. I think their solution might have something different to say though. So then all these permutations sort of lend itself to DFS. suppose I start here, then I can compare like this versus removing this. And then this. I see. Well, this is a valid string, so then it resets it to 0, but suppose this was not a valid string, then is this just the solution of this? Max of this solution plus 1, because if we're invalid, then we need to compare stuff. If we're not invalid, we reset the count to 0. And now, for example, if we did this, then previously we would well, here we just need to remove 1 though. And then I guess let's just look back to say if I remove this, or this, is there any valid? If I remove this, it's still not valid. So it's 3. If I remove this, it is valid. So it is just 1. If I remove this, is this information useful? No. If I look back and say, well, if I removed myself, then I get this, right? If I removed that's a 1, but if I remove this, it's also a 1. If I remove this, then it's a 3. Oh, actually, isn't there a much simpler way? I just write a function and check the validity, and then I just no, because you can remove multiple. It's not just one. I guess this one, not sure. But suppose you have like this, then you kind of just say, well, I know the previous one was valid, so it's the same as solving this problem. So then this is just 1. You just delete 1 and that much is obvious. And then now you're kind of back at this stage, which is good. About something like this, right? So this I can say, well, for this, why don't I just scan all the way back and then see if there's anything valid. Here, what do I do? I want to remove this and pry one of these, right? So here I'm saying, well, this isn't valid, and so if I remove this, n is not valid, and one is valid. N means I was going to say n means no valid solution found, but then you always can find a valid solution by deleting the whole string, right? So, but then I know if I delete 1 here, I'll get a, so if I delete from this index, I know I delete something here, I'll get a good situation. But I guess also, this really is like two, and you can do like max with key of length to take care of that. Here you would remove one of these and you get this. and this would be a 1. So I guess here I can look back and say if I delete this, then I'm back to this array. If I'm not valid. If I am valid, then I would just output this string with 0. And if I'm not, so for example, if I delete this, then, you know, I delete 1. Then I would just go here. So deleting 1 goes here, and then deleting the past 2 goes here. Deleting, let's say, this and this. I don't know where that would go. But for the purpose of this question, if I delete this, I would go, it means that I'm referring to the solution here. And the solution here is 1. So if I'm invalid and the minimum so far of a solution is 1, but I want to return all possible results. So this is actually a set of a tuple where you delete this and then you delete this, but you end up with this anyway. And then you delete this, which is 1, and then because if you don't delete it, it's yeah. So I would delete this, then it's just 1 plus this deletion, which is 1. So 1 plus 1 is 2. And so maybe we can do this example to see if we can derive that answer. So it's 1 and zero and I can delete myself or anything behind. But if I'm true, I can just go, right? So here I delete myself, then, so if I look back, which means I delete myself, there's no such thing as deleting like these two, right? What does that look like? Deleting these two is like, I either delete this character or I don't. If I don't delete this character, then I end up with this, which isn't valid, so I have to delete it to get to here. So it's actually, this is 1. And then now I'm here, I realize that it's 0 again. And here, I basically need to look back until I encounter 0, right? So I would say, if I don't delete it, it's not valid, so I have to try deleting it. If I delete it, then it's 1. And if you delete this or this, you still get. Okay, let's keep going. Maybe there's more cases I can look at. And then this one, we say, it's not valid, so I can say 2, because of this, and I can say because then this is just this, right? But what if I say, okay, now I want to delete this? Still not valid. Delete this, still not valid. Still not valid. But I can delete this, right? No, I can't. Still not valid. Actually, over here then, if I delete this, I get this. If I delete, you know, this, that's not good, but if I delete this, I get a different valid. So then actually here it's, you know, for example, comma, 1. No, that's 2, right? I have to delete, no. I delete this. Yeah, it's just 1. And this is a set, so. And then here, I say, if I delete this, then it's a 2. And I just keep a count of how much I delete, basically, like as my minimum. No, actually, no, we don't know the path until later. Yeah, fine. Okay. So this is talking about what? This is talking about this. So this, if I delete this, then it's just, this plus 1 and this plus 1, and then this is valid. If I delete the last character, it's not valid. And if I delete if I delete the last character, it's like this, right? So actually it's like 3. And if I remove this, it's not valid. If I remove this, it's valid. Are there any cases where you need to remove 2? I just want to see how that works. Like, and then you basically removing like this gives you this answer, and then removing this gives you this answer. So then basically you would have these two, like, you know what I mean? Like answer 1, and then it's like 1, and then answer 2, and it's like 1. Then you take your set, dp minus 1, and then you list. So basically the algorithm is you take whatever the solution was in the past, and then you compare it, like you append the current character, and if it's obviously it's valid, then it's valid. Then you just keep this because you can't do better than 0. Otherwise, if it's not valid, then I'm gonna try to remove one character behind everything, and then that'll take care of the case where if adding a new character results in removing one, will give me a good result. So in this case, like this. But I wonder if there's a case where I remove like every odd, like, how does this work, right? It's, I want to remove like this and also this. So because here we got lucky with this case where it's 1, so it's very easy to see the solution. Here it's,
I'm not sure I understand.
This, and then because the previous character, so like if this is 0, this is kind of guaranteed to be this. And then also I'll try to delete, because it's not valid, I'll try to delete this and this. If I delete this, it's just this plus 1. If I delete this, I'll also have it, but it's the same, and then this is not valid, so I won't keep it. And then for here, it's also not valid, so I'll basically have two, like removing these two, or I remove, so I delete this or delete this, it's not valid, and it's not valid, and it's not valid. And then the next one is 1, 2, 3, 4, 5. It's also not valid. So I have like 3, but also if I remove 1 over here, then I would have something that's good. And I might just pop this, doesn't matter. I'll just pop this, because it's already bigger than this, so. Or maybe not, doesn't matter. Let's keep going. So 1, 2, 3, 4, 5, 6. So here I will remove this. I find that it's not valid. This. So I remove this, then actually I get this subproblem. Seems like the algorithm could work, but I'm not sure how. There's only 3 minutes left, so I think I'll just take a shot to implement it, probably over the 3 minutes. We can start from base case. So this set is this iteration set, and then I'll just initialize it with the empty string of 0 edit distance. And then this set is this set, and then check valid of 0 to j plus 1. What happens if I is at the very last letter, then j is 0 to j plus 1 is... So j would be length of s minus 1. Okay, so that's fine. And 0 times length of S. Well, actually, if it's valid, it's just 0, right? Yeah, it just kind of discards everything else. So not valid. Then so this is valid, we'll just add this to this set. And then if it's not valid, then I just want to look behind and add everything there. So dp of so suppose we're here where I equals 2, and I'm looking at, deleting this. Oh, actually, I wonder if this works like such that, let's say I'm at 2, this is 3, so 0 to 3, and then this is nothing. So 0 to 3 just reduces down to 0 to 2, and the new S is actually the entire string, and then I'll save some work, corner case work. If not, then I'll handle this later. And then else, if I'm at, say, at like 2 here, then I'm actually at, and I want to look back one, then it's actually 2 again. And then for element in DPI, so for example here, or here to here, then So this translate this over to here when so this says delete nothing or delete one character, check the valid for every character and then add it. Actually, yeah. But if it's not valid, then I want to delete one of each character and just check its validity and then do one. So either I don't delete or I do delete, and if I do delete, I do this. And this translating into here, it's a separate procedure actually. So I'll just go here and float of infinite. I don't think I need to add anything that is bigger. Which means DFS probably could have worked. Okay. This updates my min. So you're only adding things that are candidates. So when you translate all these things over, you're really only adding things that are candidates to be considered. So in this case, you'd actually add both. That's fine. And afterwards, dp of I plus 1 is this set. And in the end, I want to loop over. Oh, I need to do check valid. So So if this is bigger than this at any point, then return false. But if we run through this whole loop and there's no point where L count and if R count and there's no point where R count is bigger than L count, which means this is strict subset or equal to L count, then that means we have more open parentheses than close parentheses, so we're good. And the part where we start with this is already taken care of. I guess we don't really need this if we have this anyway, but whatever. And after the loop is done, we just make sure that the L count and R count are equal. And if they're not equal, then that must mean we have more L counts than R counts, so return false. And yeah, so that's check valid. And then one thing I forgot to do is this. So S of J can only be deleted and considered if it's a parentheses. And well, I don't even know if you can loop through a set like this. Okay. Why does it work here but not here? So it's not a tuple. So element is a tuple, so then why is it 0? Like, this is an element, and okay. So the candidate S expands for some reason. So J is 2, so 0 to 2 is like this. And 3 and beyond should be empty, right? So oh, because the string still exists. The empty string is yeah, there's a lot going on. I feel like I should just went with DFS. Okay, that's actually a miracle. But we could have multiple things in the results. Oh, okay, but this one's easy. And let's just do a 2-pass. So 4. This n should go here, should be valid, and then oh. And yeah, that should return true. But I'm curious about these test cases. Did that change corrupt these other things? Yeah, I don't know. Yep. is lesser than the current minimum. Parentheses removed is. Let's try and rate the star valid. Okay, start with leftmost bracket. Recursion is defined by index, which we are currently processing. Okay, two different variables, left and right count. Okay. Our current character SI is either, if it's neither, then we simply add the character to find a solution in the current recursion. However, if current character is either of the two brackets, then we have two options. We discard this character by marking it as valid, or we consider brackets part of final solution. Okay, when all the parentheses in the original expression have been processed, we simply check if the expression representing is valid or not. So we do a expression check. That way, the way you check if an expression is valid or not is that was in left and right count. That's fine. Even with valid expression, we need to keep track of the number of removals we did to get this expression. So basically depth of, kind of your depth of your tree, except in this case. Once recursion finishes, we check if the current value of remain count is less than the least steps we took. If that's not the case, we don't record an expression, else we record it. I just want to see the recursive call, which is self.remaining. If it's not parentheses, we increase our index and the left and right count remains the same. And your expression appends this character. Otherwise, so this ignores the, so deleting the current character. Okay, and then if the current is the open bracket, we consider it and increment it. So left count +1, else if the current parenthesis pointer, we consider it only if it doesn't violate. Makes sense. remaining count is less than or equal to removed. Yeah, both the recursions, I guess DP was the wrong call. If I did recursion, it would just be, I don't know if I'd keep track of all these metrics. I might keep track of how many I've deleted and then skip over the, and I also need to keep track of the index. And I'd skip over the character, like non-parentheses characters, and then return I guess they're doing top to bottom, but I would do bottoms up. Like I would start with the entire string and then would just delete it recursively and delete the left and right recursively and check there, as opposed to building out the string. Okay, yeah, next time I feel like if I think recursion, just do recursion. Because DP here doesn't work with this case. Because F needs to know that it's like an F, and if I'm an F and I'm like the third character, do I just then I can do something like similar to here. Look backwards, and then if this is simpler, this set dot add plus s of j, so this current character, and I don't need to delete anything. And then here we would that might not work, because if it's sprinkled all around, then I can't just add it to the end. Else if I'm pretty unsure about this. Yeah, I think this misses quite a few combinations. So yeah, recursion was the way to go. But what I mean by recursion is for example, you would just do like new s is s of 0 to I. And then if check valid s return s, otherwise you do this and then you check valid s. So now in each layer, if it's not valid, it'll just go ahead and remove, like let's say I remove this and it's not valid, then it'll go ahead and remove like some other stuff. And then you just wrap this around like this boilerplate and you just have global logic. Or yeah, you could just have like, you know, answer or something, or answer here. And something like this. I need to probably do this because of return answer, which is an array. I'll just add it. If something like this. So then this will just say, hey, if it's a parentheses character, let's try deleting one of these. And if it's not, like if like this character happens to be not one of these, then we just pass the entire string back in, or like substring back in. And then I would just check s. And if it's not valid, I return s. And then this will return all answers of valids, but what you can do is to say, well, you could have a global variable of length. So, or you can have a global variable of answer. So for example, answer is like this, and like this, and then answer if max length or something of answer is less than or equal to s, and answer like this, something like that. And then at the end, you can't return answer, you need to return the set of list of, you need to return the set of answer into a list. But Anyway, yeah, that's this problem.